Hello, my name is Liliana Reyes, and this is Lab 5 Rope Swing for Physics 2211, Summer 2019. So the purpose of this lab is what effect does including the drag force have on our predictions? From known data from the world's largest rope swing, we'll create two computational models. The first model will include the gravitational and the spring force. The second model will also include these forces, but it will also include the drag force. Next, we'll compare both position versus time graphs using Excel to make observations. So physics principles used. So we must identify the forces acting on our system. So the system is a person on the rope swing. The gravitational force can be found by F grav is equal to negative mg. Air resistance, or the drag force, can be found by F air is equal to negative b times velocity times the magnitude of velocity. The spring force, or Hooke's law, which is F spring is equal to negative ks s l hat. And here we have a diagram of our basic structure. So we have our attachment point, which we will set as our origin for our coordinate system. And this is when the person is at rest, which you can see by this red block. And then for the next picture is when we are at rest before the person is let go from the swing. So next, initial conditions that we found on the internet and also from the videos. For the length of the rope, we have 42.75 meters or 150 feet. The average mass of a human, which is 80.5 kilograms. Spring constant we found was 30,000 newtons per meter. Our drag coefficient we found to be 1.15, which I found the average of 1.0 to 1.3 online. And for our Go script code, so without drag, we have our basic conditions. So we have our ball mass, our ball position, which we set as negative 45.72, which is 150 feet we are from the attachment point from the negative x direction. And then the ball velocity is 0 because we are at rest. Our constant, which is 9.8. Our spring constant, our relaxed length of the spring, which is our 150 feet. And then we have these next three lines to update the spring. And for our calculation loop, we have while time is less than 14 seconds, we calculate the spring force, and we also calculate the gravitational force by inputting the formulas we saw earlier, and we add these to find the net force. Next, we apply the momentum principle to update the object's velocity and the object's position. And lastly, we update the spring. So our next code that includes drag is the exact same thing. The only difference is we have our drag force constant here, and for this side we have force of drag, which we will input the equation we saw earlier, and we will add that to our FNet. So this is a look at the two models. So this is our computational model without drag. So as you can see, it does the full semicircle, and we do have our force of gravity, our FNet, and our force of the spring, which is the purple vector, and then gravity is the mint green, and orange is the FNet. And for force model with drag, we have the same conditions, and as you can see, we don't make that full semicircle here. We stop right about there, and we can say that this is due to the drag force, which slows down the motion of the person on the swing. And so next, we can look at the two computational models on Excel. So this is our model. So as you can see in the beginning, they do follow the same path and are about the same, so about 4 seconds. And then after that, they have a very big change in the two graphs, very different. As you can see, because we do not go all the way up as on the semicircle as we did on the model with drag. So we do have this big discrepancy here. And for our results, so as we saw in the Excel spreadsheet, there is a dramatic difference in the two computational models of the predicted motion of the rope swing. The model that included the drag force will probably be far closer to the actual data than the model without the drag force. And also, we can conclude that the drag force opposes any motion causing the rope swing